Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
In this problem, we're given that there's two infinitely long wires, carrying current in the same direction, separated by a particular distance. Uh, Now, let's just give a little drawing of this. So we'd have, let's draw them from the cross-sectional side. So say we have one wire here, wire 1, and it's going to have a current of 4 times what we'll call I, because that is the current that is going to be going through wire 2. Now, the current being carried in the same direction, so I'll just say the current's going into the page, and we'll call that an X heading away from us. We know and are given that the distance between the two wires is 1 meter. Okay? And we're asked along a line perpendicular to both of these, so connecting all of them. And we'll draw a little line here, a little dotted line, connecting them. The question is, where along this line, anywhere, is the net magnetic field for both wires going to be 0? Now, that is an important question. Well, actually, in order to answer that question, an important thing is to consider where the magnetic fields are allowed to cancel and where they're not going to cancel in the regions around these wires. So really we have to consider several spaces and think about how the magnetic fields are going to add up in those places. So we're going to have a region that lies between the two wires. We have to consider what the magnetic fields are going to do there. And then we have a region to the right of wire 2 we have to consider, and then the region to the left of wire 1 that we have to consider. Now, before we can decide whether or not the magnetic fields are going to cancel or not, we have to draw what the direction of the magnetic fields are going to be. If we follow the right hand rule and put our thumb into the screen along the direction of the currents, then our fingers are going to wrap around in a clockwise manner. So both of these wires are going to be creating magnetic fields, circular magnetic fields around them that are clockwise in nature, right? Right, so this would be, say, the magnetic field from wire 1, but that's going to vary with distance. And this is going to be the magnetic field from wire 2, but again, that's going to vary with distance. Now, if we look at the regions here, so in the region to the left of wire 1, the magnetic field is always heading up, the magnetic field due to wire 1 is always heading up, and the magnetic field due to wire 2 is always heading up. So the magnetic fields are always going to add to the left here. So that's not a region where the magnetic fields can cancel. And we see the same thing happens to the right of wire 2. The magnetic fields will always add because they're always heading downward along that dotted blue line. Now, in between the two wires, we see that the magnetic field due to wire 1 is heading down and the magnetic field due to wire 2 is heading up. So this is the region where the magnetic fields can cancel. And so that's the region we're going to focus on. So we need to find a location between these two where the magnetic fields will cancel. I don't know exactly where that's going to be, but I have a suspicion that it's going to be further away from the stronger, the current, the wire carrying the stronger current. So it's going to be further away from wire 1 than it is going to be than wire 2. And we're asked to calculate everything as measured from wire 1. So let's create a new variable we're going to solve for, called R1, which was going to give us the location of where this magnetic field is going to cancel. So it can vary, but we're going to just draw it on there so we know what it represents. And we have this R2 here, which is the distance from wire 2 to the point where the magnetic field is going to, the net magnetic field is going to be 0. And then, because we know that the total distance between them is 1 meter, we know that R1 plus R2 equals 1 meter. And therefore, later on, it's going to be useful to express R2 in terms of R1, and then we'll get an expression like this. And we'll see why that's important in a couple seconds. So, we've figured out where the magnetic fields can cancel, and we've defined some variables to help us figure out, so as we solve for that thing, right? We want to solve for R1 here. We want to figure out where that magnetic field is going to cancel. Now, if we know the directions are always opposite in between these two wires, we know that the magnitude, the magnetic fields are going to then cancel where the magnitudes of these two magnetic fields are equal. So ultimately, we want to solve for the expression of the magnetic field from wire 1 equaling the magnetic field from wire 2. So we go back to our expressions of the magnetic fields created by current carrying wires, and we remember that it's mu naught times the current going through the wire. In this case, wire 1 has current I1, and we divide that by 2 pi times the distance from the wire to the place we care about. In that case, the distance from wire 1 to the place we care about is R1, right? This distance here. Now, we have that equal to the magnetic field created by wire 2, which is going to be mu naught times the current through wire 2 divided by 2 pi times the distance from wire 2 to the location we care about, which is R2. But remember, what we see, a few things here can cancel across the equal sign, our mu naughts and our 2 pi's. So we're left with a nice ratio of currents to distances, but also remember, we want to solve for R1, and we have an expression for R2 in terms of R1. So we're going to plug this into here and rearrange this equation. So we see, ultimately, we have I1 divided by R1 is equal to I2 divided by 1 meter minus R1. Now, in order to solve for this, I'm just going to flip the reciprocal and solve for R1. So if I flip the reciprocal here, I get that this is R1 over I1 equal to 1 meter minus R1 over I2. Also, now is the time to plug in our currents. We know what the values of our currents are going to be. So we have R1 over I1, which is 4I, is equal to 1 meter minus R1 over I2, which is just I, and we see our I's cancel. So overall, we have R1 over 4 is equal to 1 meter minus R1. Add our R1 over, that's a 4 over 4 R1 plus a 1/4 R1. That gives us a 5 times R1 over 4 equal to 1 meter. And therefore, solving for R1, we see, and I'm going to write it over here so I get a better answer. Solving for R1, we see, or a better display of the answer here, R1, we get 4/5 of a meter, or 0.8 meters. So, given this configuration of two current-carrying wires, the magnetic fields due to both of those wires are going to cancel and have a zero magnetic field that is 0.8 meters away from wire 1, and therefore 0.2 meters away from wire 2. And that is our answer.